In this video, we're going to go through how to verify trig identities. So here are some guidelines to help us out. First, work with one side of the equation at a time. It's often better to work with a more complicated side first. Second, look for opportunities to factor an expression. Add fractions, square a binomial, or create a monomial denominator. Third, look for opportunities to use the fundamental identities. Note which functions are in the final expression that you want. Sines and cosines pair up well, as do secants and tangents, and cosecants and cotangents. Fourth, when the preceding guidelines don't help, try converting all of the terms to sines and cosines. And then fifth, always try something. Even making an attempt that leads to a dead end provides insight. Let's go to our example. So here we're going to be verifying the identity secant squared of theta minus 1 divided by the secant squared of theta to the sine squared of theta. So this is kind of our end goal. Now we look at this and we see, hey, this can be used as a Pythagorean identity. Our Pythagorean identity tells us that the secant squared of theta equals the tangent squared of theta plus 1. And so we'll take that secant squared of theta and we're going to replace it with the tangent squared of theta plus 1. So we're going to rewrite it as the tangent squared of theta plus 1. And so that goes in that spot. Then we have that minus 1 over our secant squared of theta. Now, the reason why we're not going to convert our secant squared of theta here is because we're trying to get this to be a sine squared. So we're not trying to cross everything out. Now, from this situation, the ones are going to cancel out here. Those will go away. And that will leave us with a tangent squared of theta over a secant squared of theta. From here, we can kind of rewrite this so that we get that the tangent squared of theta divided by the secant squared of theta, which allows us to keep, change, and flip. From our properties, or our identities rather, we know that the secant of theta is the same as 1 over our cosine of theta. So if we have a 1 over a secant squared of theta, and what we really have is 1 over a 1 over cosine squared of theta, which is going to be a 1 times a cosine squared of theta, or a cosine squared of theta. So we're going to replace our cosine squared of theta in for our piece right here. It's going to go in for that piece right there. So now we have the tangent squared of theta times the cosine squared of theta. And we're going to split tangent apart here because we know that tangent is a sine squared of theta over a cosine squared of theta. And remember that we're multiplying our cosine squared of theta, and put that over 1, and we're able to cancel out our cosines, which leaves us with our sine squared of theta, which was what we wanted it to equal. And so now we're finished. We have verified that identity. Let's look at another example together. Here, we'll verify the identity that 2 times the secant squared of alpha equals 1 divided by 1 minus the sine of alpha plus 1 divided by 1 plus the sine of alpha. So we're going to try and get this one as our final. So we're going to work with this side right here. So let's start by rewriting that. So in order to add these, we need a common denominator. So in order to do that, we're going to multiply both our numerator and our denominator here by 1 plus a sine of alpha, and our numerator and our denominator of this fraction of 1 minus the sine of alpha. Doing so is going to give us a 1 plus the sine of alpha over our 1 plus sine of alpha times 1 minus the sine of alpha. And we get to add that to our 1 minus the sine of alpha from the other fraction. From here, we can add our 2's together. And on the bottom, you might notice that we have matching opposite or conjugates. So if we have conjugates, we can take our a squared and minus our b squared to make this a little bit easier. So here our a value is the 1, and our b value is the sine of alpha. And so this is going to turn into 1 minus the sine squared of alpha. So from here, what that's going to give us, let's give ourselves a little bit more room than that. Let's come over here. So what we have now is we have 2, and if you take a look, our sine of alphas are going to cancel out there because one is positive and one is negative. So we're going to have 2 divided by 1 minus the sine squared of alpha, and this goes with our Pythagorean identity. Our Pythagorean identity is that a sine squared of alpha plus a cosine squared of alpha equals 1. So if we subtract the sine squared of alpha from each side, that's going to tell us that the cosine squared of alpha equals 1 minus the sine squared of alpha. And so we can plug in this value. So we can plug this in right here in for our 1 minus the sine squared of alpha. And so that gives us a 2 divided by a cosine squared of alpha, which is really a 2 times a 1 over a cosine squared of alpha. And we know that this piece right here is the same as a secant squared of alpha. And that's going to end up giving us a 2 times a secant squared of alpha.